So this talk is based on work with Simone Karen Ho, Murat Kologlu, Shota Komatsu, Peter Kravchuk, and David Meltzer. That will hopefully come out sometime in the next few months. The subject of the talk is detectors in the Wilson-Fisher theory. And I want to start by giving an idea of what I mean by a detector. And I won't start with the definition, I'll start with an example. So an example of a detector is the integral of a local operator along a null line. So here, for example, O is a local operator with spin J. We can take the spin indices of O and point them all in the plus direction and then integrate in the plus direction. And in a conformal field theory, which is what I'm mostly going to be focusing on in this talk, there's a nice way to package these null integrals of local operators called the light transform. And the idea of the light transform is to label these null integrals by a point, x, and a null direction, z. So x is a point, let's say in Minkowski space, and z is a null vector, so z squared is 0. And the picture is that x labels the initial point of the null integral, and z is the direction that the null integral is along. The nice thing about labeling these null integrals in this way is that the result actually transforms like a conformal primary. So here I'm using index-free notation. So for example, if we had a local operator, you can take its spin indices and contract them with null polarization vectors. And that gives O of x comma z. And for a local operator, O of x comma z is just a polynomial in z. This is just another way of packaging together the information in a local operator. And the nice thing is that if you do the null integral in the right way, weighted in the right way, then the thing that you get, L of O, transforms like a primary operator as a function of x and z. So it transforms under conformal transformations in the same way that this O of x comma z would.
Sorry, is it, Simon, is your integral from 0 to infinity or minus infinity to infinity?
The integral, good. The integral is over a conformally invariant contour, and that contour starts at x, and it ends at the point in the next Poincare patch with the same Minkowski coordinate as x. So that's a conformally invariant notion, because if you have 2 points in neighboring Minkowski patches on the Lorentzian cylinder, then conformal transformations move them in tandem with each other. The only conformally invariant integral contours that you can have are basically of this form, where you could go up more than one Poincare patch if you wanted to, but here we're just going up one patch because that's the simplest thing you could do. Does that answer your question?
Yes, thank you.
Good. So this first expression that I wrote here, this one, is what the light transform becomes in a particular conformal frame. So this is the conformal frame where you take, so for this expression, you take x and you send it to past null infinity. So in other words, you set x equal to minus infinity times z, and then it becomes this familiar integral. And then this other expression down here, the more complicated integral, is what it looks like in a general, in a more general conformal frame. And this integral makes it look a little bit more complicated than it is. So in the integral, you can see that when alpha is minus infinity, the integration point starts at x. So this is the integration point. It starts at x, and then when alpha goes to 0, it diverges to infinity. And that's this part of the contour here. And in a conformal field theory, infinity is not a special point. And indeed, it looks like something funny is happening with this weight factor here. But the weight factor turns out to just cancel the factors that you would get by doing a conformal transformation to bring infinity to a regular point. And so there's actually no branch cut at alpha equals 0. And the correct integral prescription for the integral is to just continue the integral beyond alpha equals 0 over to alpha equals plus infinity.
Sorry, David, in embedding space where time is a periodic coordinate, this contour is sort of like a closed contour? Is this right?
The embedding, that's a good question. So the embedding space is actually a double cover of Minkowski space. And so in the embedding space, the starting point of the contour would have embedding coordinate p, and the endpoint would be minus p. So they're not precisely the same embedding coordinates. They only become the same once you mod out by the additional z2.
Okay, thank you.
Sure. Okay, good. So this is just a fancy way of writing a null integrated local operator. But a nice thing about it is that written in this way, it becomes a conformally invariant integral transform. And actually, and I'll call it the light transform, and the light transform changes the quantum numbers of the thing it's acting on in this way. So if you start with a primary with dimension delta and spin j, you get something that formally transforms like a primary with dimension 1 minus j and spin 1 minus delta. And you can check for yourself, if you like, just as a sanity check, that if you compute the Casimir of the conformal group, so that's delta times delta minus d plus j times j plus d minus 2, then this is actually invariant under this transformation. And so it has a chance of being a conformally invariant transform. Okay, so that's some useful language for us that will come back again.
So why was
yes.
it expected that the Casimir would be invariant under this change?
So
because
the claim
you
is
could
that
go to some other operator also.
The claim is that this is a conformally invariant integral transform. So it should commute with the conformal generators, and in particular, it should commute with the Casimir built out of the conformal generators.
Okay.
This is kind of it's a close cousin of the shadow transform. We'll actually talk about in a little bit, which might be a more familiar example of a conformally invariant integral transform.
Sorry, David. If I doubled up your contour, so I did it sort of twice.
Yeah.
Then it would become closed in embedding space. Is this right?
Yes. Yes,
and
that's right.
Then would it no longer be labeled by a position x? Would it be, should I then think of it somehow like a closed contour?
The position x is still significant because of the way the integral is weighted.
Okay.
Yeah. In other words, it doesn't just become a function of that closed contour. It also depends on the base point on the contour. The amount of data that it's labeled by is still x and z, point in the null direction. Okay, so this is just something you can do with a local operator, and the notion of it as a detector has to do with a conformal collider experiment in the language of Hoffman and Maldacena. So the idea is to think about these kinds of observables in a detector frame. So this thing here is a poor man's Penrose diagram for Minkowski space. So it's not exactly a Penrose diagram because I've decided to make, so in a Penrose diagram, usually the spheres are collapsed to a single point. So here I'm making manifest a circle of which you can think of, I'm making manifest a circle for one of the spheres. So in this diagram here, this entire circle around here is in a conformal field theory identified with a single point, which is spatial infinity, sometimes called I0 or just infinity. And the idea is to think of this as a detector, you should take a local operator and integrate it along a null line at future null infinity. So in the language of the previous slide, what that means is that we take the light transform of O and we set the initial point of the light transform to be infinity, this point at infinity, so that the initial point is here at spatial infinity, and then the integral goes from spatial infinity up to future infinity. In this frame, the remaining data that you have to specify to say where you're putting the operator is this null vector z. And we can write z in this form. I should have mentioned that these operators L of O and O are all homogeneous functions of z, so I can rescale z and write it in this form. And then n here becomes a point on the celestial sphere. So n labels the direction on the celestial sphere where we place this operator. And then there are these important observables called event shapes, where you basically measure the expectation values of these operators in some state. So here we have a state psi, which forms both the ket and the bra. And I've inserted in the middle a product of a bunch of light transformed operators at different points, z sub I, on the celestial sphere. And by the way, so remember that z is a d-dimensional vector that's null. So you can think of this as an embedding coordinate for the celestial sphere. So it's an embedding space coordinate for SD minus 2. So formally, this event shape looks a bit like a conformal correlator in a fictitious d minus 2 dimensional CFT. That point of view on the kinematics will be helpful for us at a few points in the talk. Okay, so probably the most famous of this type of observable are energy correlators. And that's an example where we take the light transform of the stress tensor. So we insert null integrals of the stress tensor. And that has the interpretation as measuring the energy that propagates out in different directions. So the z labels the direction on the celestial sphere that the energy is propagating out to. And you can compute a correlator of the distribution of energies at future null infinity in some state psi. So the interpretation in conformal collider physics is that the state psi is created by some kind of collision of particles, which you can think of as some operators acting on, it's a state given by some operators acting on the vacuum, and then you measure the energy correlators in that state. Okay. So this is an example of a detector. Again, before proceeding to a definition, let me give a slightly, let me give another example of a detector, which is in a free theory.
Sorry, David, probably a vague question.
Yeah.
By measuring this, the integrated energy, you're not keeping track of all the information that you might have wanted, because you're not keeping track of when the energy came out. Right?
That's precisely right.
Can you do better somehow? Can you?
Yeah. That you absolutely can. So you can basically, instead of doing an unweighted null integral of the stress tensor, you could try doing some kind of weighted integral. That's right. You can do that. So these unweighted null integrals will turn out to fit into a nice framework that I'm going to explain over the next few slides. But I think there are lots of open questions about more complicated types of integrals you could do and how to make sense of those in a non-perturbative CFT. So let me maybe return to that closer to the end of the talk if you want to ask it again.
But this
Good.
transform that you described, is that the only way of making a conformal primary? Something that transforms like a conformal primary?
Yeah, that's absolutely right. So that maybe I should have said that. So that's one very special thing about this type of transform. The resulting operator behaves like a conformal primary, whereas if you did something more sophisticated, it wouldn't behave like a primary, and you'd have to do a bit more work to classify it, to understand where it fits in the spectrum of the CFT. Okay, yeah, thank you for that comment. So let me give another example of a primary detector, which is in a free theory, instead of doing the integral of the stress tensor, we could consider the integral of a higher spin current. So here's a higher spin current with spin J. Actually, the real higher spin current would be some combination of derivatives acting on two phis with J free indices. And so I'm here, I'm just writing it in a schematic way. and you can take the light transform of this thing and stick it at future null infinity. In a free theory, we can ask what this detector does. One way to characterize that is to write down the vertex associated to this detector. So I'll define a vertex in this way. It's basically the expectation value in a single particle state. The vertex of this detector takes the following form. And so it's some integral of delta functions, and the best way to interpret it is in words. In words, what this detector does is it counts particles moving in the z direction, so particles that are propagating out to a particular direction on the celestial sphere, and it weights them by a power of their energy. So for example, when j is equal to 2, then we have the stress tensor, and what we're doing is we're counting particles propagating out in a particular direction, and we're weighting them by their energy. But when j is equal to 3, we're weighting them by energy squared, and so on. So this is a natural thing to do in a free theory. But if you turn on interactions and you try to make sense of an operator like this, it doesn't make sense because it's not an IR-safe observable. So the intuitive test for whether something is IR-safe is to imagine a particle propagating out to infinity, and it splits because of some interaction. So it splits into, it splits off soft radiation, it splits into other particles, and you can ask if the observable you're studying is relatively insensitive to this splitting process. In a strongly coupled theory, the splitting process will happen over and over many times, and if your observable is very sensitive to it, then things will get out of control and your observable won't be well defined. And indeed, if we think about computing something like the energy squared, whereas in a splitting process, the energy is conserved. So if we're just computing the energy propagating out in some direction, it has a chance of making sense even if there are many, many splitting events. But something like energy squared just doesn't, because it's very sensitive to the number of times splits occur, because energy squared isn't conserved during these kinds of processes, these soft radiation processes. So that's the intuitive explanation for why this isn't an IR-safe observable. And indeed, if you try to just stick this observable in a matrix element in a perturbative theory that's not a free theory, then what you'll find mathematically is infrared divergences. Okay, so you'll encounter IR divergences if you try to do anything other than j equals 2 with this kind of observable. Now, there's, I think, a nice analogy for how you should think about this situation.
Sorry, Dave, the IR divergences are because the observable goes to 0 in the deep IR, right? Not infinity.
Yes, that's right. So well, yes. Roughly speaking, yes. I think I'd like to answer the question after explaining this current slide. But yes, that's right. The IR divergences don't mean it's infinity necessarily. They're indicating that they're really an indicator that your observable is bad and you need to fix it. And that's what I'm going to explain on this slide. But was there another question?
Yes. If you move instead the detector a little bit inside, would you be able to cure it?
No. That's a good question. I guess it depends on your interpretation of the detector that you move slightly inside. Let me read this. Let me go through this slide, and then I think that will help frame the discussion. So the idea is that these divergences are something that they're analogous to something that we deal with all the time in interacting conformal field theories. And I think this interpretation of IR divergences was really eye-opening for me when I started thinking about things this way. I really like it because it really resonates with the way I think about local operators in conformal field theories. So I found this really interesting to think about, and I hope you will also find it interesting. So let's think about a local operator in an interacting theory. We can think of it as a perturbative CFT if we like. So, so what is a local operator? Well, we should think of a local operator as roughly anything that you could measure at a point. The meaning of that phrase is really a theory-dependent thing. It's not something that you get to pick before knowing the theory. And that's sort of the theme of this slide. The theory, you have to let the theory tell you what its good observables are. So suppose that you have some perturbative CFT and you try to write down a local operator just in terms of the fundamental fields. If you do that, you'll encounter UV divergences, right? We're well aware if you write down some bare operator, then there'll be UV divergences associated with that bare operator. And what does that mean? Well, you have to renormalize the operator. So you encounter UV divergences, it just means that your operator was bad and you need to define a renormalized version of the operator. Through that renormalization procedure, you discover a space of operators that's now theory dependent. So the good operators of the theory depend on the theory. You have to let the theory tell you what the good operators are. You have to start doing a calculation and see what the good observables are in the theory. So once you've identified the space of good observables, once you've identified the local operators, then you have lots of beautiful structures on these local operators that make sense non-perturbatively. Like, for example, the operator product expansion, which is something that's really best understood in terms of the good observables, the true local operators of the theory, and not the bare operators that you would write down if you were just starting to do perturbation theory in a naive way. Now, in the case of the space of local operators, we also have a non-perturbative characterization of the space of local operators using radial quantization. So in radial quantization, the space of local operators gets interpreted as the Hilbert space of the theory on SD-1. Now, the situation with detectors has a lot of similarities, although the analogy isn't quite complete, as I'll explain in a moment. So the idea with the detector is you should think of it as anything, roughly anything you can weight a cross-section with. So the role of a detector is to measure things in a state. And so it's measuring stuff at future null infinity, and it's anything that you can measure at future null infinity. Now, if you try to write down a detector in a naive way, then in a perturbative theory, you'll encounter IR divergences. And what are those IR divergences telling you? Well, they're telling you that your detector, your bare detector is a bad observable. You need to redefine it by renormalizing it. And once you renormalize it, so you encounter these IR divergences, you renormalize the divergences, and you find instead a theory-dependent space of good detectors. So the claim here is that every theory has a space of good detectors, which are the things that you are allowed to measure at future null infinity, and that's a theory-dependent thing, and you need to let the theory tell you what it is. Once you've identified the non-perturbatively well-defined detectors in the theory, then you get some interesting structures relating those things to each other. One of them is the light ray OPE, which I've worked on recently, and I won't have time to talk about it much during this talk, but I would certainly be happy to answer questions about it. But the question marks here are because we really don't know the full space of relationships between these types of detectors. And one of the reasons for that is, in the case of detectors, we don't have an analog of radial quantization. We don't have currently a Hilbert space interpretation of these detectors. That's something that's currently lacking, and I think that would that could give a huge amount of insight into what's going on if there was some non-perturbative characterization of these things.
I have a question, David.
Yes.
So in a gauge theory, which is conformally invariant, let's say n equal to 4,
yeah.
Would you think that null Wilson lines are good detectors?
So I actually will talk about. I'll actually talk about that later in the talk. I'm going to talk in detail about null Wilson lines.
Okay. Yeah. Thank you.
Sure. Other questions?
Hi, David.
One. Sorry.
Sorry, go ahead.
Yeah, one way to take this discussion, can I say that in the previous slide, the current that you integrated over for j greater than 2 is not a current in the interacting, is not a conserved operator in the interacting theory. So, so could you think of the renormalization as renormalizing that local operator and integrating it?
So absolutely. So one example of a detector is the integral of a local operator. And in that case, this renormalization procedure is just the renormalization of that local operator. But as I'll talk about next, the space of detectors is larger. So it contains more than just that procedure. But you're absolutely right. In the case where you have the integral of a local operator, it's just renormalizing that local operator.
Thank you.
Hi. So was there anything very specific about stress tensor? Is it that it is IR safe if you take that?
Yeah, so right, the stress tensor is, in some sense, doesn't need renormalization. Well, if you define it, I think it probably depends on your regularization procedure, but yeah, roughly speaking, the stress tensor is always a well-defined local operator, doesn't have an anomalous dimension, and therefore you don't have to do anything special to it in the interacting theory.
So if some operator is still conserved in the interacting theory, like if I take a proper conserved current, then you will see similar things that probably that will be still IR safe.
I mean, I think you have to worry about whether your regularization procedure respects whatever conservation conditions you have on your operator. But yes, if you're working in some formalism where you have an operator that's truly protected, then you won't encounter divergences.
Oh, thank you.
Hi David. Sorry, probably a stupid question. This observable when seen in Minkowski space looks very special, but seen on the this contour that you've chosen, the one at Scribe Plus, looks very special. But is it special viewed on the Lorentzian cylinder, on the Minkowski, the cylinder? Yeah.
So the special thing about the contour from the point of view of the cylinder is that it starts and ends at points that are related to each other in a special way. So there's a special relation between a point and the point in the next patch with the same Minkowski coordinate as it. That's actually a conformally invariant notion because it's actually in the embedding space. It's taking the embedding coordinate to minus the embedding coordinate, which is a conformally invariant thing to do.
Okay,
so that's the special thing about it.
Right. So we don't need to think of it as in this Minkowskian way to realize. To understand that the fact that it has that it's not well defined is just general. You see clearly from thinking of this as Scribe Plus, but it could be any 2 points on the.
Yeah, that's right. So, for example, the notion that these are IR divergences is a conformal frame dependent notion. If you worked in some other conformal frame, you would find that there are other kinds of divergences. It's some mixture of UV and IR divergences.
Yeah, thank you. Oh, sorry, one more, maybe stupid. Again, going back to your Minkowski patch kind of view.
Okay.
You would think that if you had a detector that was sort of like what Abhijit was asking, if you had a detector that was approaching Scribe Plus,
yes.
then you get something finite and would go to 0 with some power that depends on J and a coefficient outside that. And you might think that coefficient was the observable. Is that?
Yeah, that's roughly the idea. So if you think about local operators, one way to define good local operators is to take some local operators that you know about and scale them toward a point and pick off the coefficient of the thing that is scaling like a power as you do that. So that same procedure would work in this case. You need to you want to scale things towards this configuration and pick off coefficients of power laws, and that will be another way of defining detectors.
It's sort of like the way we define observables and operators in ADS-CFT. Right? You strip off the divergent parts as you go to infinity and the coefficient of that.
Yeah, that's right. That's right. Okay. Okay. So.
Yeah. Good. Sorry. Can I just make a very small clarification? I mean. So these detector observables that you're defining, would be a closed sector. That's what you're going to say that, the OP closes among themselves, or like?
So like I said, I don't know the full space of these detectors. And what I'll tell you about next is a structure that they fit into, but I don't know if it's the complete structure.
All right, I see.
Okay, good. So someone, maybe it was Abhijit, asked about the case where your detector is just the integral of a local operator. And in that case, there's nothing particularly surprising about the notion that you can renormalize it and define a good detector, which is the integral of the renormalized local operator. There's a surprising fact in conformal field theory that detectors lie on Reggeized trajectories that are analytic in spin. So these local operators are associated with integer spins. There are detectors associated with the local operators, but the claim is that there actually is a larger space of detectors, which include things at general complex spin. And in a free theory, it's easy to see what these detectors are. So in a free theory, remember that we were counting particles weighted by e to the j minus 1. Because energy is positive, we're free to pick j to be any complex number we like, and we get a good detector in a free theory. The surprising thing about this claim that detectors lie on Reggeized trajectories is that you should be able to renormalize even a detector with a complex non-integer value of j. So if you write down this detector that in the free theory counts particles with powers of e to the j minus 1, where j is a complex number, you should be able to define the detector in a careful way so that it makes sense even in an interacting theory. This is something that people have observed in perturbation theory, that you can do this in examples. But if you're just working in perturbation theory, you might always wonder whether the thing that you're doing actually makes sense. And for local operators, we know that we should be able to renormalize them in a consistent way because we have this non-perturbative characterization of local operators in terms of the Hilbert space of the theory on SD minus 1. The nice thing about analyticity and spin is it is a different way of giving us that confidence for the space of detectors. So analyticity and spin tells us that there should exist detectors with general complex spin, and therefore when we renormalize detectors with general complex spin in perturbation theory, we are doing something that can actually make sense non-perturbatively and be consistent. So this observation that the spectrum of a CFT could be extended to be analytic in spin was made by Karen Ho in an amazing paper a few years ago. Subsequently, Peter Krawczyk and I gave a general non-perturbative construction of these detectors with general J. The construction shows, roughly speaking, it shows how they arise, but it doesn't. But the actual spectrum of these things, what they look like, what they do, is a theory-dependent thing. And one of the points of this talk is to try to explore the space of these detectors with general complex J in the simplest example theory that we might think of. And that's the Wilson-Fisher theory for this talk. And we'll find some interesting structures in that theory that I hope will be instructive for larger explorations.
David, hi. I was just wondering whether the light ray operators that are associated to the local ones, whether they form some kind of closed algebra amongst themselves under, say, like the light cone OPE, or is it that you're forced to add some of these, the ones with arbitrary J?
That's, let's see, that's an interesting question. So if you consider just, let's say you start with local operators and you consider null integrals of local operators, and you try to make sense of a limit where you have two null integrals that come close to each other. So in that limit, you can produce these more general light ray operators. You'll produce them actually always with integer spin j, but it'll be the wrong integer spin. So you'll produce spin 3 operators on the even spin Reggeized trajectory, for example. So you at least are forced to sort of add those, excuse me, to the theory if you want to make sense of this kind of light ray OPE. Another thing you might want to make sense of is a kind of Reggeized OPE, where you take two operators and you boost them very much with respect to each other. And in that limit, all this full structure of light ray operators would enter. So I guess it depends what limits you want to consider, whether or not you need to add these new operators. And I should say that the algebra of these new light ray operators, we have no idea what it is. We don't know what it closes on.
Okay.
So there might be other things that you would want to add.
So even the notion of the algebra is not, I mean, it depends, as you said, on what kind of OPE you take, or is there a canonical, is there something canonical about any of?
The most general thing that you could try to ask is to decompose the space of operators, not necessarily local, all non-local operators in a CFT into conformal families. And that is something that I think we're very far from being able to do. The space of all operators, not necessarily local operators, is much more complex than the space of local operators. And I guess one of the lessons here is that there's stuff hidden in there that we didn't, that is still mysterious and interesting. But that's the sort of general program you would have to do. You want to take the space of operators, which is roughly speaking the Hilbert space tensor, its star, and classify conformal representations living in there.
Okay, thanks.
Sure. Okay, so right, so what is this larger structure that these detectors that are analytic in spin live in? So one way to think about it is in terms of a Chu-Frauchi plot, where we plot the spectrum of a CFT in a kind of funny way. So on the y-axis, we have spin j, and on the x-axis is delta. And it's useful to plot delta minus d over 2. And I'm kind of abusing notation here. People usually define that as being I times nu. I'm going to just write nu for delta minus d over 2. So I apologize for that. So on this plot, you can put the local operators of the theory. So for example, the stress tensor would sit here at spin 2 and dimension d. And then you could have higher spin operators, like the lowest risk higher spin operators would be out here, and so on. So those are the dots on the plot. And the claim is that if you instead of thinking of local operators, you think of their light transforms, they fit into this larger structure of Reggeized trajectories that are analytic in spin. So that's what these lines are here. This is an example of a Reggeized trajectory. The general light ray operators that I mentioned before, they inhabit these Reggeized trajectories. And the special thing about them is that when you take one of these light ray operators and you set j equal to, in this case, an even integer, you get back the null integral of a local operator. And so this is the general structure, but we don't know very much about what this Chu-Frauchi plot actually looks like, and that's one of the points of this talk, to try to explore the Chu-Frauchi plot in an example theory.
David,
but there's one,
sorry.
Yes.
Sorry, the labels on the plot, are they according to the local operator that would have given rise to this light ray operator?
Yes, that's right. So Abhijit may be remembering that this light transform had this property of swapping the quantum numbers around. And I am labeling the operators by what the local operator would have been. That's the conventional way of labeling them.
Thank you.
Good. So there's one reason for choosing these coordinates is that this plot has a nice symmetry called shadow symmetry. One nice thing about viewing the things on the Jufraci plot as light ray operators is it makes much clearer what shadow symmetry in a CFT actually is. There's a different version of the shadow transform which which makes sense in Euclidean space, and the problem with that version of the shadow transform is that it's unclear why there should be, well, so let me just say what shadow symmetry is. So it's a left-right flip in this plot. And it's implemented by a conformally invariant integral transform. So it's another one of these integral transforms, kind of like the light transform. And what the shadow transform does is it just manipulates the null direction associated with a light ray operator. So the picture is you have a light ray operator pointing in some direction, and the shadow transform kind of smears out the direction that it's pointing on a null, so that it kind of becomes a light cone operator instead of a light ray operator. And the smearing is, so here there's an integral over z prime, and z prime is the direction argument for this O. And the smearing is done in a conformally invariant and in fact Lorentz invariant way. And what this integral transform does is after the light transform takes you here to these quantum numbers, the shadow transform takes you further to these quantum numbers, and you can kind of see that the thing that's underlying this transformation is this delta goes to d minus delta thing. And the shadow transform is its own inverse, so it goes back and forth, and it defines a symmetry. It gives you a symmetry of the space of light ray operators. And this shadow symmetry will play an important role a little bit later. But I want to emphasize one of the surprising things about it. So and it also makes clear something wrong with the language light ray operators. So one of the interesting things about an interacting theory, and we'll understand sort of how this works in a moment, is that the Reggeized trajectories for over here that are associated with null integrals that are associated with light rays can be analytically continued over here. And I just said that this part over here, this shadow part, these are associated with something more like light cone operators, where the null directions have been smeared along a cone. And so it tells you that you can analytically continue between light ray operators and light cone operators. And so in some sense, we should probably call them all light cone operators. But this is kind of mysterious. You can ask, like, how do you go between light rays and light cones? And that's something that we'll see in a moment when we look at an example. Okay. Any questions about that, about the shadow transform or the Jufraci plot?
Sorry, Dave, my internet was unstable. I missed what you said about light cone operators. Could you repeat that for a minute, please? What is a light cone operator?
Sure. So the statement is that the shadow transform is a symmetry of this plot. And what the shadow transform does is it takes an operator that's localized on a light ray and it makes it localized on a light cone by smearing it over the cone. The interesting thing about the Jufraci plot is you can actually analytically continue from things that are supposed to be localized on a ray to things that are localized on a cone. So in some sense, you can't really distinguish between them. In the non-perturbative theory, it doesn't want you to be able to tell the difference between things that are localized on a ray or a light cone.
Thank you.
Does anything special happen at delta equal to d by 2? I mean, when nu is 0?
Yes. So that is that's the point of the next part of the talk.
Okay.
Okay. So that's what I want to talk about next, and I'm going to talk about it in an example of the Wilson-Fisher theory. So this point is interesting because the operator that lives at this point, it's called the Pomeron, and it controls the leading behavior in the Reggeized limit of basically any observable. So you take any blobs, any objects, any operators, and you boost them with respect to each other, the Pomeron controls the leading behavior in that limit. The reason, and you can see why from this formula. So this is a formula taken from a paper called Conformal Regge Theory by these people. And the statement is that in the Regge limit, correlators involve an integral over spins and dimensions. And the integration contours are such that this point here, the Pomeron, is the point of sort of maximal spin along the integration contour. So the integration contour is some imaginary contour that you can imagine being perpendicular to the picture that I drew. The Pomeron is the point with maximal spin along that contour, and the spin is the thing that controls the growth in the Regge limit. So the Regge limit would be something like t goes to infinity in this cartoon. And so it's the highest spin along that integral contour in J that controls the Regge limit. So the Pomeron, as far as I know, has been sort of a vague, ghostly concept lurking in the QCD literature for many years. And one of the nice things about this perspective is it will really let us write what the Pomeron is and just see it and hold on to it and do whatever we want with it. Okay, so the Pomeron is the thing that sits at delta equals d over 2. And the thing I want to explain next is what this Pomeron actually is in the Wilson-Fisher theory. To do that, let's start in the free theory. So in the free theory, the Chu-Frauchi plot looks like this. It's just a pair of 45-degree lines. This 45-degree line is the Regge trajectory corresponding to the higher spin currents in the free theory. And here for simplicity, I'm just talking about 2 phi operators. So the operators in the free theory can be classified according to phi number, and I'm just looking at 2 phi operators for simplicity. So we have the null integral of the stress tensor here, the null integral of the spin 4 current here, and the analyticity in spin tells us that we have a whole trajectory. And then shadow symmetry means that we also have this other 45-degree trajectory here. And very explicitly, we can write the vertices for these operators. So remember, a vertex in my notation is the matrix element in a one-particle state. So the matrix element for this 45-degree trajectory, the one that the light transforms of local operators live on, looks like this. And in words, what it does is it counts particles propagating in the z direction, and it weights them by some power of their energy that depends on nu.
Your plot includes only those light ray operators that are built out of integrals of local operators?
No, so the integrals of local operators would be here, and so on. So it includes the full Regge trajectory that goes through those points and the shadows.
But couldn't there be other light things off those lines that were not?
Yes, yeah, there could, and I'll talk about them. But these are yes, you're right. So let me talk about the other features of the plot later. For now, I'm just focusing on these 2 lines.
Yeah, thank you.
Sure. Okay, so this is what the first 45-degree trajectory does, and then we can look at its shadow trajectory, and that has a vertex that looks like this. So what does that mean? Well, it gets contributions from particles with null momenta, so that's this delta p squared. P is the momentum of the particle that is being detected. So it gets contributions from particles with null momenta, but it doesn't get contributions from only a particular direction on the celestial sphere. It gets contributions from all directions. Instead, it weights the particles by some function of the angle of propagation. It's some function of where they hit on the celestial sphere, but it's not a delta function. Okay, so this thing is local on, oh, I guess I already said it. It's local on SD-2, but its shadow is non-local on SD-2. And again, the cartoon for that is just what the shadow transform does. The shadow transform takes a ray, and it smears it out over the null cone. So we have these two things. In the free theory, the trajectories seem to just pass through each other.
Sorry.
Yeah.
Even though the shadow thing is non-local, the weighting is such that it's still labeled by a point. It's still labeled by an x mu.
Yes, that's right. So yes, for an analogy, for a very close analogy to that, you can think about the shadow transform in Euclidean space, where this version of the shadow transform where you integrate 1 over x minus x prime to the 2d minus delta times O of x prime. So this is an integral of an operator, so it's non-local, but it's labeled by a single x. So it's analogous to that. In fact, it's exactly the same transform, but written in embedding space coordinates for d minus 2 dimensions.
Okay, yes, thank you.
Sure. Okay, so in the free theory, we have these two trajectories. Now, there's actually a subtlety here that I'll get to in a moment, but let me talk about what we expect to happen in the interacting theory, which is that these two trajectories that pass through each other should undergo some kind of recombination process and turn into a pair of trajectories like this that miss each other. And there's actually an example of this that's well-known in gauge theory that has to do with these BFKL and dGlap operators that I'll try to explain in a few slides. But the idea is that, so this recombination is not a theorem. It's like a folk theorem, or maybe not even that, it's lore. The idea is that Reggeized trajectories should not cross because interactions should cause some kind of level repulsion. But this is not a theorem because there's no Hilbert space in Hamiltonian that makes this level of repulsion idea precise, as far as I know. But that's the folklore, and indeed we'll see this happening in our example. But this presents kind of a puzzle, and this puzzle is related to the thing I was talking about before with light cones versus light rays. So these, this 45-degree trajectory here is associated with light rays. It's counting particles propagating out to a particular direction. And this one is associated with light cones. It's counting particles and just weighting them by the direction, by a function of the direction that they propagate out. And it's interesting to ask how these two things could possibly mix with each other in order to recombine. So that's one of the things that we'd like to understand. Okay, so let's really look at the point delta equals d over 2. Let's look at our two trajectories here. And so that's the same as nu equals 0 in the coordinates I chose. And so we can set nu equal to 0 and look at the vertex for the first 45-degree trajectory, and that's this. And we can do the same for its shadow. And then the next step is to stare really hard at the formulas. And if you stare really hard at them, you'll notice that there's actually something funny going on, which is that the vertex for this shadow trajectory is not actually well-defined. It's not well-defined because it's, what you get is actually a bad distribution. So correlation functions in Lorentzian quantum field theory have to be distributions, which means that they have to be well-defined when integrated against certain classes of test functions. And in this case, we should have something that is a distribution in both Z and P. And it turns out that the thing we get is not a good distribution. The analogy you should have in mind is something like 1 over x, which can't be integrated against the test function. What this means is that we've actually misidentified what the operators are at nu equals 0, and we need to take a more careful look. We need a more careful look at the nu equals 0 operators, even in the free theory.
Sorry, for this operator, the spin turns out to be 1, right?
The spin is close to 0 for this operator.
In the free theory.
In the free theory, it's not precisely 0 because we're working in 4 minus epsilon dimensions. But if we were in 4 dimensions, it would be spin 0.
Spin 0.
Yeah. That would, yeah, you can see on the, on the Ciuffracci plot, the idea is the stress tensor in 4 dimensions would live at delta equals 2, j equals 2. So a 45-degree line would hit the origin.
Oh, okay. But you're, yeah, okay. In the graph, you have moved the origin a little bit.
Yeah, that's right. So this graph would be appropriate for 4 minus epsilon dimensions. The
I
intersection moves up slightly.
Okay, thank you.
Thanks for that question.
Sorry, maybe related. So this operator is in the free theory is weighting particles by e to the power what power?
So the shadow operator is not weighting operators according to their energies. It's weighting them by, well, it's not just their energies. It's also weighting them by some function of the angle that they hit the celestial sphere. It's this function. It's this function here. And so the problem.
Sorry, the Pomeron was a shadow operator.
No, I haven't said what the Pomeron is yet.
Yeah. Okay. But is there a non-shadow operator at delta equals d by 2?
Yes, the non-shadow operator is this first one, and yes, you're right. That one is weighting the particles by a power of their energy.
The power is this minus 4 by 2.
I think that there's an off by 1 thing from the power. It's actually a little bit tricky to derive because you need to divide by the norm of the state, and I haven't done that here in these formulas. We can figure that out by looking at the formula for the spin j thing, which I wrote earlier. Sorry for going so fast here. Let me find it. So what we should do is the exponent, write the exponent as j plus d minus 4, and then the weight, the thing it's weighting it by is e to the j minus 1. So we write this is equal to whatever was in the exponent there, which I think was maybe d minus 4 over 2, and solve for j.
Okay. I suppose I wanted to understand from this point of view why this operator was ill-defined in the free theory. Was it a special?
So I would need to explain what's going on with this distribution, why it's bad. So the bad thing is actually the angular direction on the celestial sphere. So if you look as a function of angle, this thing is, so there's this minus 2 z dot p to a power minus d minus 2 over 2. So
sorry, I'm sorry to interrupt, but maybe my confusion, the top line here was well defined. It's the bottom. This is v tilde that was badly defined. Is this right?
Yeah. This is this one. Yeah, it's just v tilde. That's right.
So v itself is fine. So sorry.
Yeah, v is fine. Yeah,
Thank you,
this one is okay.
Thank you.
Hi.
Yes.
So this Pomeron operator is the one that is leading in the Reggeized behavior. So even in free theory, you want to be able to identify what that is by just looking at the Reggeized behavior of correlators. That's in free theory. What that operator is.
Yeah, I'm not sure what the role of this discussion is in the free theory. So there's an interesting operator in the free theory that we have not written down yet, and I'm going to write it down on the next slide. I'm not sure whether that operator actually enters correlators of the free theory, but it does become it becomes completely crucial when you turn on interactions and everything starts mixing, because then it absolutely does enter correlators of everything.
Right. So it's not clear if that operator actually contributes in Reggeized free theory, in strictly free theory.
Let me write down what the operator is first,
Okay.
and I think that'll help actually.
Okay.
The point of this slide is that I actually have not written down the full space of operators at nu equals 0. I've written down something that isn't a good operator, and I was going to explain why that is. So this minus 2 z dot p thing. So here, if you think of z and p as being null, then when z and p approach each other on the null cone, z dot p goes to 0. And so we can write a coordinate in this angular direction. So maybe the best way to do this is this thing here is an SD minus 2, and let's pick stereographic coordinates on the SD minus 2. And then what this becomes is x to the absolute value of x to the minus d minus 2 over 2, where x is the distance between these two things in stereographic coordinates. And you should think of this thing as being kind of like 1 over x in one dimension. So this is in d minus 2 dimensions. I guess, sorry, this is x squared to the minus d minus 2 over 2. So it's a thing that has a logarithmic divergence when it's integrated. And the logarithmic divergence in this case comes from the angular direction of the integral. So if you tried to take this operator and you tried to integrate against the test function of z or p, in other words, if you had some kind of wave function for a particle that wasn't that was supported over a range of null momenta, then you wouldn't get a well-defined number. And so that's bad because it contradicts properties that we need correlators to have in the Lorentzian quantum field theory, and we need to fix that. Let me give a brief.
Sorry, David.
Yeah.
Sorry, it seemed like it was okay in the one dimension. In higher dimension, it seemed problematic.
No, well, so first of all, this direction, this angular direction, only appears in 3 or higher dimensions.
Okay, sorry, I may have misheard because I heard one dimension at some point, but yeah, okay.
Sorry, I was making an analogy to 1 over x, the distribution.
I see. Okay, fine.
Yeah, 1 over x can't. Yeah. Okay. Okay. So let me explain a little more what I mean by bad distributions and how we fix them. So, okay. So let's think just about functions on the real line. So for this slide, x is just something on the real line. There's a nice family of distributions which are powers of x. So we'll look at p lambda of x, which is x to the lambda minus 1 times theta of x. So this is a power of x, and there's a theta function restricting x to be positive. So if real part of lambda is bigger than 0, then this is a well-defined distribution, and in fact, it's holomorphic in lambda. So that means we can integrate it against a sufficiently nice test function, let's say a Schwartz function, and we get a nice number. And if we do that for, if we fix the Schwartz function, then we get a family of numbers that depend holomorphically on lambda. Now there's a theorem that says that if you have a distribution with this property, then it can actually be extended to a meromorphic function of lambda. So it can have poles if we go away from the region where it's most nicely defined. And in this case, if we try to analytically continue this distribution to lambda equals 0, the first thing we encounter is a pole at lambda equals 0. And that pole has to do with the fact that 1 over x times theta of x is not integrable. And the pole is proportional to a delta function of x. And so that makes sense because the non-integrableness of this distribution comes from an infinitesimally small neighborhood of x equals 0. Now, this thing is a meromorphic function of lambda. So it has a Laurent series. And the next thing in that Laurent series is something that I'll call the plus distribution, which is a kind of regularized version of 1 over x. And in words, the way the plus distribution is defined is that you integrate against 1 over x and you subtract off the log divergence. So the plus distribution is well defined as a distribution, whereas 1 over x is not. But there's a kind of price that you pay, which is that this regularized version of 1 over x doesn't transform under scaling the way that you expect. So if you just chase the definition of this thing, use this identity and pick out the definition of this plus distribution, you find that it has a non-homogeneous transformation law under scaling. Okay? So this is the way that we'll fix the problem with the shadow operator that we wrote down before. We'll take this bad distribution and we'll replace it with a regularized version. But when we do that, there's this subtlety of this inhomogeneous transformation that we're going to have to deal This was for functions in one dimension. And then the idea for our situation is we should think of the x direction as being like the separation between two null directions on the celestial sphere. So think of this as being like x, and that will be the analogy that we use. So let's go back to our shadow operator that we had before. We had this thing raised to the minus d minus 2 over 2, and the way to fix it is to use this plus distribution instead. The plus distribution, as I said, is funny because it doesn't transform under scaling in the way you expect. In fact, it's not homogeneous under scaling. And what that means is that if we just take this thing and replace it with the plus distribution, we actually, it doesn't make sense with dimensional analysis. So to make dimensional analysis make sense, we need to stick in a mu. We need to stick in a scale. So we stick in a 1 over mu here and the power of mu up front. That's good. Now we have something that makes sense under dimensional analysis. But there's another problem, which is that it doesn't transform irreducibly under Lorentz transformations. This is maybe a little harder to explain, but roughly speaking, you could imagine you take the z direction, and if you do a boost that preserves the z direction, then it rescales if you do a boost in the z direction, it rescales z by some overall factor. So a boost is kind of like a dilatation on the celestial sphere. And this thing transforms inhomogeneously under that. And that means that this object doesn't transform in an irreducible representation of the Lorentz group. We have to fix that. We can fix it by adding a different thing that also transforms with a shift under a boost. And that shift cancels the shift associated with the plus distribution. So let me say that again. So we need the plus distribution to make something that's actually well defined. We need to introduce a scale for consistency with dimensional analysis, but then we also need to introduce this inhomogeneous term to get something irreducible under Lorentz transformations. And when we do that, we end up with this monster operator v tilde prime 0. And the claim is that the space of operators living at nu equals 0 in the free theory is actually the traditional 45-degree Reggeized trajectory continued to the origin on the Ciuffracci plot. Maybe I said that poorly, but it's just this operator that I said was good, this one, the okay one, and not v tilde, but this crazy thing, v tilde prime. So those are the good operators of the free theory. And an interesting fact about them is that they actually form a log multiplet under dilatations. So even in the free theory, there's this interesting logarithmic multiplet of detectors sitting at nu equals 0. And the free theory has just told us, these are the good detectors, these are the things you're supposed to measure in the free theory. So this is something you could measure in a conformal collider experiment if you were a free theorist, if you lived in a free world, then this would be a thing to measure. And now we can see that there's this interesting multiplet structure, and it's maybe not too surprising that once we turn on interactions, this log representation splits into two different irreducible representations. So basically, we get when we renormalize this thing, we get some anomalous spin, and that causes these two operators to get split in the vertical direction in the Ciuffracci plot. So if you renormalize these things, you find that the renormalized operators there are two of them. They're different linear combinations of v and v tilde prime. And the one with the higher spin eigenvalue is the Pomeron. So the Pomeron is some linear combination of v0 and v0 tilde prime.
Hello. Yeah, is there some sort of a vague sense in which at least in d equal to 4 or 4 minus epsilon, you can think of this as the new operator as some kind of the light cone transform of phi square log phi.
I don't think so. I don't think there's a log phi, but I think you could think of it as, in terms of formally putting in like a log of a derivative.
Log of a derivative.
Yeah.
I see. You mean phi log derivative phi?
Yeah.
Mm-hmm. I see. Okay, thanks.
Sure. Yeah. Other question?
Yeah. You told us how in the free theory, I mean, even staying away from this, the special value of nu, you told us how in the free theory, the light operators were integrated energies over a line. Is there an intuitive way of saying what the shadow operators are in terms of integrated energies over a surface? Is it just integrated energies with some funny weighting factor?
Yeah, absolutely. Yeah, in fact, for the stress tensor, if you do the light transform and then the shadow transform, then you get the integral of the stress tensor over a surface, and that turns out to just be the conformal multiplet of the conformal generators.
Sorry, my internet was unstable. I couldn't quite catch it, but please go on. I'll catch it.
Okay. All right. Well, good. So the next part of my talk is kind of is on a different aspect of the true-Fauci plot and is relatively self-contained. And I can see that I'm pretty far over time. So I'm wondering if maybe I should stop here.
No, go ahead. How long do you think you would need?
Well, I'm not sure. Maybe 15 minutes.
Yeah, that's fine. Go ahead.
Okay. Well, since it's Zoom, people can easily enough leave without worrying that anyone will know. Okay. Fine. Great. Okay. So I'll continue a little bit. So so the point of this is to try to understand what's going on at nu equals 0 in the true-Fauci plot and understand the operator that controls the leading behavior in the Regge limit. But we're also interested in other kinds of features that the true-Fauci plot can have. In other words, what are the other detectors that exist in this theory? And there's an interesting class of detectors that's inspired by this question that I think maybe Spenta asked earlier about integrals of about Wilson lines. So let me review for a moment what's going on in gauge theories. So the plot on the left is the true-Fauci plot of a weakly coupled gauge theory. It contains these same 45-degree trajectories as we were talking about, because it has, in the free limit, it has higher spin currents. So the stress tensor and the other higher spin currents live on a 45-degree Regge trajectory. But there's also this interesting horizontal trajectory at j equals 1, and this is the so-called BFKL trajectory. At zero coupling, these things just cross each other. But the lore is that when you turn on the coupling, they should recombine, and indeed this is what happens if you do calculations. So if we zoom in on this intersection point, the 45-degree trajectory and the horizontal trajectory recombine into a pair of trajectories. So what this means is that you should look at this picture, you should look at the leading Regge trajectory in the free theory as being something like this. So there's a 45-degree part, and then there's this part and this part. And that's the thing that sort of retains its identity when you turn on interactions. And then there's this beautiful story about what happens when you go to stronger and stronger coupling. This thing, this sort of funny cup-shaped trajectory starts to flatten out like this. And eventually at strong coupling, it becomes this almost flat trajectory where the middle part is moving up. Okay, I skipped something here. So this, I'm just talking about the planar theory. So actually very little is known about what this looks like in the non-planar context. But in the planar theory, this middle part moves up towards spin 2, and the parts on the other side of the stress tensor move down, and in the infinite coupling limit, you just get a flat trajectory at spin 2. So this is the picture in a gauge theory, and the example you could have in mind here could be like n equals 4 supreme Mills theory. So let me, what I'd like to talk about for the moment is what these j equals 1 operators are, and in particular we'll be interested in whether there's an analog of these things in the Wilson-Fisher theory. And one of the reasons that asking these questions is interesting is because this is relevant for the true fate of the Regge limit of these theories. So at weak coupling, it's actually these gauge theory that are most important for the Regge limit. We'd like to make sense of the physics of this. So let me explain
David,
what, yeah.
The Pomeron in this case is totally different from what you talked about so far, right?
Yeah, that's right. That's right. So presumably in a gauge theory, there's a similar thing going on here. But in a gauge theory, it would be a subleading effect in the Regge limit to these horizontal trajectories.
Thank
you. Okay, so what is this horizontal trajectory? It is related to these null Wilson lines. So the idea for making the horizontal trajectory is you take a Wilson line from spatial infinity to future infinity. So it runs along a null line, along future null infinity. But a Wilson line itself is not a gauge invariant operator because it's not starting and ending at the same point. It starts at this point and ends at this point, which are different points. So to make something gauge invariant, we actually need 2 Wilson lines. So we can do one here and one here at different positions on the celestial sphere. But, and then we can contract the gauge indices here and here. So remember, this whole circle is spatial infinity. It's all a single point. So that gives us a gauge invariant operator, but now it's labeled by 2 points on the celestial sphere. So it doesn't transform irreducibly under Lorentz transformations. And the way to make it transform irreducibly is to integrate it against some carefully chosen wave function in the angular directions. And the correct choice here is a 3-point function in a fictitious d-2-dimensional CFT living on the celestial sphere. So that's what this thing is. It's a 3-point function in a fictitious CFT. So it's just the famous formula for 3-point functions. Here it's written in the embedding space. So this is going to be products of things like 1 over z1 dot z2 to some power times other dot products of z's. You do this integral in order to project onto a particular irreducible representation of the Lorentz group, which is the conformal group for the celestial sphere. Once you've done all of this rigmarole, you end up with a gauge invariant operator that transforms irreducibly under the Lorentz group. And this is called a Reggeized gluon operator. This gives you a horizontal trajectory in the true Fracci plot. And the way to understand that is to sort of squint and think about this null Wilson line as being kind of like the light transform of the gauge field. And the gauge field, of course, isn't a gauge invariant operator, but we're gonna squint. We're working in perturbation theory. So the gauge field has spin 1. And so this basically is what it looks like is kind of like the light ray OPE for null integrated gauge fields. And there's a rule for the light ray OPE that the effective spin of the operator you get in the light ray OPE is the spin of the first operator plus the spin of the second operator minus 1. And in this case, this is 1 plus 1 minus 1. So this is J. So you get something with spin 1. And then delta is a parameter that you get to pick here in this wave function. So you can put in different deltas. And for every delta that you put in, you get a different operator. And so that's why you get a horizontal trajectory on the true Fracci plot.
Sorry, David. If I think about it from the celestial sphere point of view, then I would have thought the operator that would appear in the OP of these operators would have any delta. That's why you can pick any delta here, and any spin, right? I mean, I could have chosen a weight function so that the resulting operator has some higher spin also, or I couldn't have.
Right. So you're asking about weighting the path, weighting the integral in a different way, and I think that if you want a gauge invariant operator, you're not allowed to do that in this case.
No, I mean this p delta, this thing that you have here in the integral, the capital P
you're
delta
talking about
-1.
spin. Yeah, you're talking about spin on the celestial sphere. So that's, importantly, that's a different quantum number. And I'll talk about that a little bit later. So let me draw a Young diagram that might actually help. So there's a, if we draw control multiplets, the first row has length minus delta. The second row has length J, capital J. And it's actually the third row that's controlled by the thing you just mentioned.
I see.
I see. The light transform swaps the first two rows, but doesn't touch the third one, or the higher ones.
I see.
So yes, that's a good point. So it's actually only the scalars on the celestial sphere. So I call this thing transverse spin. It's spin on the celestial sphere. It's actually only little j equals 0 that gives rise to interesting operators in this way. And that's actually an interesting story that I can tell you more about later.
So if you pick some non-zero j, then you don't get a, what is the statement that you don't get a good detector operator, or what do you want to say?
Yeah, so I actually don't know the answer for this in the gauge theory case, but I do know the answer in the Wilson-Fisher case, and it might be analogous. So in the Wilson-Fisher case, the statement is that if you pick a non-zero little j, you actually get something that's re-expressible in terms of the other parts of the Chu-Fauci plot that we've already talked about. And it actually becomes the light ray OPE, which is convergent for higher little j. But the way we would get new operators is by identifying things that have new IR divergences. So you need to find things that are that have IR divergences and require renormalization. Maybe I'll try to explain that a little better in the Wilson-Fisher case a little later.
Hi, David.
Yeah.
So the connection between the null Wilson line and the light ray operator, is this a statement about one loop?
The connection between can you ask the question again?
Yes. So you mentioned the relation between null Wilson lines and the light ray operator built from gauge fields. So is this like one loop statement, or?
This is like a free theory. This is like free field statement. The reason I wrote, this is in quotes, and I wrote it down in order to be able to do this little computation here to tell us what spin this thing has.
Right, but is there any systematic way of understanding this null Wilson lines more generally, let's say at the planar level, in terms of any null operators? Is there any connection?
Well, the statement is they should really be Wilson lines. So these are the Wilson line operators make sense even in interacting theories.
Yes. Yes.
You should actually put Wilson lines along these null contours.
And you can also build null operators, let's say with the corresponding current operator. But is there any connection between them? You didn't mention anything of that sort.
Is there a connection between null integrals of the current and Wilson lines?
Right.
They're different. Yeah, they're not the same thing.
Okay.
Okay, so we can try to mimic this construction in the Wilson-Fisher theory using actually the idea that roughly the idea that you just mentioned, where instead of using Wilson lines, which we don't have, we integrate local operators. The idea here is that these Wilson lines kind of count gluons that are propagating out in these directions. So instead of counting gluons, we're going to count phi's. We're going to count particles, phi particles. Let's consider a product of these two light transformed operators in this kinematics. So the initial point for each one is the point of infinity, and they're sitting at two different points on the celestial sphere. This is the same kinematics associated with the light ray OPE, which is something I've written about before. The interesting thing here is that the light ray OPE, a product of null integrated operators like this is finite if and only if there's a condition on the spins of the operators. And the condition that you need is that J1 plus J2 is bigger than J0 plus 1, where J0 is the Regge intercept of the theory. So if that condition is satisfied, then this product can be re-expressed in terms of other operators on the Jufraci plot. And that's the content of the light ray OPE. But this is a situation where this is not satisfied. And that's actually interesting and important for us. So here we have J1 and J2 are both 0. And so we have 0 plus 0 is bigger than, so J0 is the position of the Pomeron, which is a little bit greater than 0, and then plus 1. So this is really not true. And so that means that what we're doing is we're taking a product of these two light transform things and we're trying to at the same point. And we're getting a divergent, we have a divergent quantity. And so it means it needs to be renormalized. And because it needs to be renormalized, it has a chance of giving rise to a sort of new kind of intrinsic operator in the theory. And so the idea is to take this thing and renormalize this product. And then once we do that, we get an operator that's labeled by two directions. And then we have to do the same trick as before by smearing it against the appropriate wave function to get something that transforms irreducibly under the Lorentz group. And when we do this smearing, we have a parameter delta that we can stick in, and in this way we can get a horizontal trajectory. But this horizontal trajectory lives at spin -1 instead of 1. So it lives at spin j effective is 0 plus 0 minus 1, which is -1. And then when we renormalize this thing, there'll be some anomalous spin associated to the renormalization, and the trajectory will move in some way. And we'd like to figure out how it moves. This is the type of thing that we'll look at. And let me explain.
David, can I ask? I mean, just maybe
Sure.
a very silly question, but is there any connection of this construction of these light ray operators, Wilson lines, with the Alde-Maldacena construction for n equal to 4 Yang-Mills theories, where they introduce Wilson lines also?
Oh, let's see. Are you talking about from correlation functions to Wilson loops, that paper?
No, I think they introduced this polygon of Wilson lines.
Okay. Right. So the one role that Wilson lines play is in n equals 4 superseding Mills theory. Wilson loops, null polygonal Wilson loops are dual to scattering amplitudes.
Right. That's right.
Yeah, that's right. I'm not sure. I think that picture might make clear why these null Wilson lines would appear in the Regge limit, would control the Regge limit, although not totally certain. But I think that, so if you took a scattering amplitude and you took the Regge limit, you could think about that in the dual Wilson loop picture.
Yes, yes.
And try to understand what happens. And I think you might see in that way why how these Reggeized gluons appear, but I'm not sure. It's an interesting question.
Okay, thank you.
Sure.
One more question, David. Sorry.
Yeah.
So if you repeat this construction here for some current, let's say in the free theory, then I would imagine that the OP converges. And then the statement would be whatever you get here somehow should be decomposed.
Sorry,
stuff.
Yes, that's right. That would be the statement.
If you take two currents, yeah. But then, so what is confusing? What does it mean? This decomposes into two, because what you get is some local, some conformal representation which has some delta and some fixed j, Now, what does it mean that it decomposes into? Because
Yeah,
it's some irreducible representation.
That's right. So what you get is that so the statement is, if you take this product of light transformed operators, it depends on these two directions. So we can kind of reverse this harmonic analysis and rewrite this as an integral over delta and a sum over little j of some kind of function of delta and j times some effective operator that depends on delta and j, and is a function of a single null position, and then this is also integrated over z against a wave function with the two z's in it. So this is sort of the inverse to this transform that we do here. The claim is that in the regime where the light ray OPE converges, this stuff is actually a meromorphic function of delta with poles in the right half plane, and you can deform the contour to wrap those poles and turn it into a sum.
Oh, I
And
see. Okay.
when you do that, the things appearing in the sum are precisely other things on the two-Fauci plot.
Thank you.
Sure.
Hi, David. Just to come back to Alderman-Lasena for a minute. So if you take correlation function of, let's say, gauge invariant operators, let's say currents, and then if you sort of separate them in null directions, then roughly you get a Wilson line following Alderman-Lasena. So I was just expecting that if you now integrate over these currents on a null directions, like you make a light ray operators from these currents. And if you take the correlation function of currents and separate the currents in null directions, then that gives the Wilson line, a polygonal Wilson line, polygonal null Wilson line following Alderman-Lasena.
Well, I think an integral of a current is not the same thing as a Wilson line. You're thinking of it, perhaps you're thinking of it in terms of.
So I'm beginning with just correlation function of current operators.
Yes.
So far I'm not integrating over their
Oh,
location.
okay, a correlation function. Yeah. Good.
Right. So now if I take two of these operators and make them null separated in a suitable manner, then I get a Wilson line, a polygonal Wilson line following Alderman-Lasena. Now, so this is a formula. Now let's say now we integrate over instead of just separating them along null directions, you take the currents and now integrate over their location in a null direction. So this is why I was expecting maybe there could be very close connection probably along. Now the left hand side, say the side in which you're integrating over the location of the currents, you are getting light ray operators. So I was expecting that probably there might be a connection between these light ray operators of currents and the Wilson lines, probably null Wilson lines.
Yeah, I think that makes a lot of sense. Yeah, I mean, there's this paper from correlation functions to Wilson loops that talks about limits of operators becoming null separated in gauge theories, and I think in that picture you might be able to derive the appearance of these Reggeized gluons in the Reggie OPE. Yeah, thanks for that comment. Good. So okay, so I just wanted to explain the physics of the renormalization of this operator. So I've written down the thing that we want to study, which is this crazy product, renormalized and smeared against a wave function. And now I want to explain what happens, where the divergence comes from when you try to renormalize this thing, because there's an interesting physical picture associated with it. So this is the kind of diagram that you have to compute. The divergence comes from a two-loop diagram. So the picture here is that you have some initial state, which is given by, it's a two-particle initial state and a two-particle final state. And because we're computing an expectation value, we have some, the initial state involves a time-ordered product, and the final state involves an anti-time ordered product. And the way that appears in the picture is that there's a time fold in our picture. And the time fold you can think of as happening at future null infinity. So time goes up, you get to future null infinity, then time goes back down. And our detectors sit on the time fold because they're sitting at future null infinity. And they're sitting at some positions on the celestial sphere. So the physical process that gives rise to the divergence is that one of the particles comes in, and due to interactions, it splits into other particles. So it splits into 3 particles. And 2 of the soft radiation particles get detected by the Bayer detector. So these 2 soft radiation particles hit the Bayer detector. This other one flies through and ends up in the final state. Then the soft radiation particles are absorbed by an interaction by something in the final state. So what this means is that you can have Bayer detectors sitting at certain positions on the celestial sphere, and you can have particles that appear to propagate off into different directions, but somehow are still detected by the Bayer detectors. And it's because the Bayer detectors are detecting their soft radiation. So this jives with the intuitive picture of where our divergences come from. They come from splitting events. They come from particles splitting. In this case, the fact that particles can split as they propagate out to a null infinity leads to this interesting effect. And the key property of this effect is that it's non-local on the celestial sphere. So because the splitting happens, because the particles can split and move into different angles, you can end up with detectors over here detecting particles that look like they're going over here. So that's a bunch of words, and in formulas what you find is that there's a divergence, so 1 over epsilon divergence, and it's proportional to an integral of the same kind of detector you started with, but times an interesting angular kernel. And this is a kernel that mixes up the 2 directions and turns them into 2 other directions. The kernel you can think of as being like a correlation function on the celestial sphere, and so it's natural to write it in terms of conformal cross ratios, and it has this form. So it's some combination of cross ratios, U and V. This kernel gives rise to the anomalous spin of this detector. So what we should do is take the kernel and decompose it using harmonic analysis. The way you do that is you take the kernel and you integrate it against a 3-point function, a conformal 3-point function. And because the kernel is conformally invariant, it commutes with the Casimirs of the conformal group, and therefore the result should just be a number times a conformal 3-point function again. And that number is the eigenvalue of the kernel. This computation is probably familiar to those of you who've worked on the SYK model. So you can read off the eigenvalue, and a sort of interesting thing happens, which is related to the questions Abhijit was asking before, which is that for little j equals 0, for spin 0 on the celestial sphere, you get an interesting non-trivial eigenvalue for this kernel. And that tells you that the operators with 0 transverse spin, the scalars on the celestial sphere, need to be renormalized, and the renormalized thing becomes a genuinely new operator in the theory. But if you look at non-zero transverse spin, there's this kernel actually has 0 eigenvalue there, and that is related to the fact that the light ray OPE converges in that case. So therefore, there's no sort of new operator in the theory. The correct or normalized thing can just be re-expressed in terms of other operators. So let me conclude with the resulting picture. So we've looked at the Pomeron, which is the thing that's happening here. It's the leading operator in the Reggeized limit, and it's the thing with the highest spin on the Giuffracci plot if we sit at delta equals d over 2. And then what we've just learned about is the existence of some trajectory that sits at j equals -1 at tree level. And when we turn on interactions, it gets an interesting anomalous spin. And the anomalous spin changes it in the way indicated here by this little red cartoon. So the anomalous function of this direction, nu is delta minus d over 2. And the function was something like sine pi nu over 2 over nu times cosine pi nu over 2 squared. And that's the thing that's being plotted here with these red lines. So one comment here is that this construction of horizontal trajectories with spin -1 actually works for any scalars in the theory, not just phi squared. And one can argue that these phi squared ones are the only ones that get an anomalous spin at leading loop order. So what this means is that there's actually an infinite number of trajectories here. Oops, I did a really bad job drawing that. There's actually an infinite number of trajectories here. And so the fate of all these trajectories is very unclear. And the fate of the theory in the Reggeized limit is unclear from this picture. But the part that we expect we can trust is the part with positive anomalous spin. So for example, this part here. So here, there's just one trajectory that gets a positive anomalous spin at leading order in perturbation theory. And so that should be the first subleading correction to the Reggeized limit. And that should be a trustable computation. But what happens at spins slightly lower than that is totally unclear.
Sorry, I thought the Reggeized limit was to be dominated by the Pomeron, right?
Yeah.
So when does it, so are there OPs when the Reggeized OPs when the Pomeron is absent and then it's controlled by this other guy?
Well, the idea is that these other things would control subleading corrections in the Reggeized limit.
Ah, okay, I see. And when you say this exists for all scalars, can we take just phi also?
That's a great question. So phi is kind of a funny case. This doesn't seem to exist for phi. We didn't figure out how to get a good an interesting operator by doing the same thing with phi and not phi squared.
What is not clear is how to renormalize these things, or
or even how to define them. So even if you just try to define the null integral on its own for phi, it's not actually well defined. And the right definition for the light ray operator associated to phi is actually that you should think of it as being the shadow of the null integral of the phi cubed operator.
Oh, I see.
It's related to the equation of motion of the theory.
I see. So can this construction be done also for the shadow integrals, where L theta is a shadow integral? I mean, this light cone operators.
I am not sure. At tree level, I don't think there's anything else you can do to get at something that transforms like a conformal primary. Not with two kinds of operators. Once you start talking about more operators, like 3 local operators, null integrated, and then smeared against something, then I really don't know what happens.
Okay, thank you.
Okay, so I'm sorry for going really way over time, but so I'll just flash the future directions slide. I think that it turns out that there's a lot of interesting physics to explore, even in a very old theory like the Wilson-Fisher theory. And it's interesting to explore these things in perturbation theory because it tells us something about the good observables even in weakly coupled theories. And I think that one interesting direction here is to understand these similar types of questions, for example, in nonconformal theories. For example, in something like QCD. What are the good detectors of QCD? Can we, for example, take the LHC and expand it in the space of QCD detectors? And what would that look like? So that's I think, an interesting question. So that would be an interesting direction to go. I think that these kinds of constructions can make sense even in non-conformal theories, although a lot of the mathematical tools would not be present or would be harder to use. So I'm not exactly sure how one could proceed other than by studying perturbative examples like, for example, in this talk. In conformal field theories, the structure of the Schufraci plot is important for understanding physics at large boost. It's also relevant for understanding which sum rules exist. So maybe you got a taste of this from Dollymill's talk. The existence of these non-perturbative sum rules is closely tied to what is and isn't well defined in these kinds of light ray OPE kinematics. And so that's important to map out. Yeah, and so, well, there are a few other questions on the slide, but I'll let you look at them and you can ask me about them if you like. So I'll stop there. Thanks a lot.
Well, let's all unmute and thank David for a very, very nice, wonderful, wonderfully clear talk. Questions?
David, you started your talk talking about scattering and how how you could use these light ray operators to characterize the states of a conformal field theory in Minkowski space as the stuff goes very far away. Now, I was wondering whether one could try to achieve a complete characterization of these states using these light ray operators. Something that would not just characterize them, but label states and allow one to write down sort of the analog of completeness relations for S matrices.
Yeah, that's a really interesting question. So maybe a baby version of that question that is, I think, still interesting is to think about something like eigenstates of the average null energy operator. So the average null energy operator is maybe the simplest example of one of these detectors. The average null energy operators at different angles commute with each other. And so you can try to simultaneously diagonalize all of them. And an eigenstate of that would be some state with a particular pattern of energy propagating out to null infinity. And that would be one interesting way to try to label states. And you could additionally label them with, I mean, these other types of light ray operators could potentially commute with each other. I'm not sure about that for light ray operators that are not null integrals of local operators, but anyway, there could be some maximally commuting set of them, and you could try to simultaneously diagonalize those and use them to label states. And that seems like a very natural thing to do from a scattering amplitude point of view. But I don't know exactly what to how to proceed from there, but it seems like a nice structure.
And just a quick follow-up on that. Let's say in n equals 4 Yang-Mills, people compute things that seem closely related to S matrices by just computing Feynman diagrams and then using dimensional regularization. Yeah. And these things have very nice mathematical structure. It doesn't look like they're computing nonsense. Right. Can you see a relationship between what they do and these things?
Yeah. Right. So that's something that. So I've asked Juan about this question, and so I can. Gosh, I'm trying to figure out how to add a page to this. I can't figure it out. So I've asked Juan about this, and so maybe I can tell you what he told me, because I don't know the answer. But his suggestion was that those things that people are computing that they call scattering amplitudes can be interpreted as the expectation value of a particular kind of operator. And the operator that you would have would be, not the same thing that I've been discussing, but maybe closely related. Basically, you would have null Wilson lines, so they would be a lot like these Reggeized gluons. You'd have null integrated Wilson lines for the final states to make the final state gluons, and you'd have null integrated Wilson lines to make the initial state gluons. And so what is this thing? It's kind of like one of these Reggeized gluon operators, but you have lots of things meeting at the at this point of infinity. So it really kind of looks like a star. Like there's the point of infinity, and there's a whole bunch of Wilson lines coming out of it. And so it's really just one object. And you have this one object has to be renormalized in the same sense that all the operators I've been talking about today have to be renormalized, because if you just write it down as a bare operator, it's not well defined. It has divergences, for example, associated with all of these things sitting at the same point at infinity. And those are the IR divergences of scattering amplitudes. So this is an operator that must be renormalized, and once you renormalize it, presumably it has, I guess, a one-point function, and that one-point function is the amplitude.
I see. When we normally talk about perturbative scattering amplitudes, we say that they have Wilson lines going off from the gluons to infinity. Are these those Wilson lines?
Yeah, okay, yeah, let me think for a second. So yeah, maybe I wasn't careful enough here. So I think that so first of all, yeah, so there's the LSZ prescription.
Yeah.
There's a different version of the LSZ prescription that one probably should use here, where instead of integrate, so in LSZ prescription, usually you integrate over a big region of space-time, and you Fourier transform and pick out some pole. So there should be a version of the LSZ prescription where instead you just integrate over a null line at future null infinity weighted in an appropriate way. So that's the first simplification. And then if you are, if you have something gauge non-invariant, then what you need to do is you need to connect it to a Wilson line that goes somewhere. And the natural choice of Wilson line would be, in this case, I think, going to spatial infinity.
Right.
I think that's right. Now, I would say it's spatial infinity because that seems like a nice reason for this that he explained to me once that I can't remember. But if you ask him, I'm sure he'd be happy to explain. So the idea is that you would have Wilson lines connected back to spatial infinity along null lines, and the integral would be along a null line as well. So maybe the picture would look kind of more like this. Oh, sorry. So the dot dot dots are directions that you're integrating along, and the Wilson lines are the solid lines that connect to spatial infinity.
Okay.
So
Thank you very much. Yeah.
Perhaps something like that. So yeah, so that, yeah. Yeah, I have to say, like, it doesn't, if someone just handed me this thing and said, hey, this is my favorite operator, can you compute something with it? I would say, why do you want to know about that operator? So personally, I think it would be nice if there were some non-perturbative characterization of why these are so nice. And I think in scattering amplitudes, one of the key bits of structure for why we care about them is these are completeness relations, like you mentioned. And I'm not really sure what the fate of completeness relations are in a non-perturbative theory, but perhaps there's some
But
way.
the kind of thing the S matrix people do have completeness relations, right?
In perturbation theory, certainly they do.
So we could hope that that carries through.
Yeah, we could hope that. I guess it's tricky because the things that people in S matrix community compute, the amplitudes they compute are zero, because of the Sudakov logarithms make the R divergences mean that the exclusive amplitudes are just zero. So you renormalize them and you get this stuff with beautiful structures. So I'm not sure if there's a completeness relation that survives at finite coupling.
Okay, thank you. Yeah.
Sorry, can I just ask, slight clarification of that previous question? So, I mean, you can imagine, let's say you are not in a gauge theory, for instance, you're in something like this Wilson-Fisher theory or, some other theory where there is no, you're not talking about a gauge theory as such. In that case, also, presumably you can define something like scattering amplitudes, in the same way, in a dimensional regularized way, right? So in that case, would you still expect that such objects would be given by expectation value of observables, some kind of observables? And would those observables be, in some way related to this light cone, things that you're defining?
Yeah, I think so. I think that in an interacting CFT, probably anything that you try to define, any kind of S matrix you try to define will have, if you define a bare S matrix, you'll encounter IR divergences. And when you renormalize them, the correct interpretation of that is that you're defining some kind of sophisticated operator, renormalized operator. And it would look something like these pictures.
I see. Yeah, but probably there's nothing, natural in that theory like the Wilson loops. It will be some kind of non-local operator, I guess. Yeah,
it would be some kind of non-local operator. I mean, I kind of wonder what's natural about the Wilson loop operators also.
All right, I see.
I mean, well, maybe that's a sort of an unfair phrase. I think that so in n equals 4 super mills, these null polygonal Wilson loops are, there's clearly something. Well, they have some really beautiful mathematical structure.
Yeah, they have some properties, yes, right.
And they're good observables. I mean, they are observables in the theory, and so that we should compute them, and we can match them in ADS-CFT and do all sorts of wonderful stuff with them. So I'm not saying they're bad in any sense. I guess what I don't understand is why they are, what is the non-perturbative definition of an amplitude that tells us it really should be called an amplitude.
Yeah, it's just
Does that make sense?
It seems to me that something like Kutkowski's rules are what would tell you that it looks like an S matrix, right?
Mm-hmm.
It seems to me that that's the answer somehow. That was what would make it interesting to me.
Right.
I see.
By the way, David, I'm curious. Do you guys also compute the anomalous spin for the Pomeron and the epsilon expansion?
Yes. So yeah, I didn't explain the computation, but yes, you can compute the anomalous spin for the Pomeron, and there's actually a kind of nice story there where I'm sorry for scrolling. I know it's kind of disorienting. I'm trying to find the picture that I drew. Oh yeah, okay, so this picture here. So there's some anomalous spin here that you can compute in perturbation theory, and these Reggeized trajectories, they get renormalized at 2 loops. So you get some anomalous spin here that naively would go like epsilon squared, but because of the way diagonalization works with these log representations, there's an interesting square root that appears, and you end up with an anomalous spin that's order epsilon. And that is interesting because it's related to the, confusingly enough, to the epsilon operator. So there's so the picture that one gets looks like this, and this point here is is j equals 0, so it should have something to do with the scalars in the theory, and indeed this location here is the dimension of the shadow of the epsilon operator. I guess I should call it the phi squared operator. And so you can write kind of an ansatz here of like a degenerate hyperboloid being resolved into non-degenerate hyperboloids. And so from this quantity, which is the anomalous spin that you can compute by renormalizing this thing, you can then compute this quantity, that size there, and you reproduce the dimension of the phi squared operator.
I see.
So it's sort of, it's a funny way of seeing why the phi squared operator gets an anomalous dimension of order epsilon, whereas everything else gets an anomalous dimension of order epsilon squared. It's sitting near this degenerate point.
I see. Thank you.
Yeah, and by reverse engineering, we could have known the anomalous spin in this case because we know the dimension of epsilon.
Yeah.
Sorry, of phi squared.
Any more questions? Okay. It's quite late, I guess, already.
Okay. Yeah.
So, well, thank you very much, David, again for a very nice talk. It was great.
Okay.
Thanks a lot.
Yeah, thanks a lot, and thanks for all the good questions.
Thanks a lot, David. Thank you for staying up so late.
No problem. It was fun.
Okay, great. See you.
All right. Bye.
Bye.